Welcome back to Fundamentals of AC Circuits. In this video, we're going to discuss series parallel RC circuits. The learning objectives for this video are that you will be able to understand the sinusoidal response of an RC circuit, calculate the total impedance of an RC circuit, be able to apply Ohm's law to an RC circuit, and analyze an RC circuit. And more specifically, the focus of this video is that you will be able to analyze series parallel RC circuits. You already know what a series parallel circuit is, and a series parallel RC circuit is just going to be the same thing as a series parallel circuit, except now we have both resistors and capacitors that will be shown in your circuit. And we can have various types of combinations of your resistors and your capacitors, but we will have a combination of resistors and capacitors, and now we're going to have to start to identify relationships that are in series and relationships that are in parallel. And we're going to have to apply the concept of impedance as we collapse that circuit. So if you look at the circuit on the screen, if every component you saw was a resistor, you would know to collapse these two elements here, collapse these two elements here, and then collapse the total together. Well, we don't have resistors, we have resistors and capacitors. So now we're going to have to still combine impedances, but we're going to have to use what we discussed in the previous video about series RC circuits and parallel RC circuits to collapse each relationship. So if you look here, Z2, these two components have a parallel relationship. So we're going to have to combine R2 and C2 using the formula provided in the previous lecture for a resistor and a capacitor in parallel. We'll have to combine that impedance together. Z1 is R1 and C1 in series, so we'll have to combine those together using the formula for series relationships. Once we combine the two components in Z1 and the two components in Z2, well then this total impedance will then be in series with this total impedance. Z1 will be in series with Z2. Well, how do we combine Z1 and Z2? Well, Z1 will be written as a polar quantity and Z2 will be written as a polar quantity. What you're going to do is convert those both to rectangular in order to add them together. Then you'll have to convert that back to polar in order to calculate your total current and then move forward with calculating any other values that you need to find within the circuit. So, we're going to analyze a series parallel circuit by looking for relationships. Look for things that are in series and combine them using our formula for components in series. We're going to look for things that are in parallel and use our formula to combine impedances that are in parallel. And then we're going to have to use phasor math to combine each individual impedance in this circuit to get a total impedance. So here is an example of a series parallel circuit with the same orientation that you just saw on the screen. We're going to find pretty much everything we can possibly find in this circuit. We're going to look for the total impedance, the total current, the voltage across every component. We're going to look at the phase angle for the total current. We're going to draw a phasor diagram for every voltage in this circuit. And then we're going to find the current through R2 and C2. So we're going to begin with total impedance. This is already giving you a clue of what to start with. Obviously, R1 and C1 are in series. That's a series impedance. R2 and C2 are in parallel. That's going to be a parallel impedance. So we'll start by calculating Z1 and Z2. But before we can do that, we have to know the capacitive reactance of C1 and C2. So we're going to start there. We're going to use the frequency that's provided on the diagram and then the value of each capacitor to calculate that capacitive reactance. Now that we have these two values, we can begin to figure out what Z1 is and then what Z2 is. So we'll start with Z1. Our formula for a resistor and capacitor in series is R minus JXC. So I'm going to convert everything to ohms. So I have 1,000 ohms minus J, 313.31 ohms. Here's our total impedance for Z1. And here it is in polar form. Next, we're going to find the total impedance for Z2 using the formula for a resistor and capacitor in parallel. So when you plug in your values for R2 and XC2, you'll get 479.86 at an angle of 45.12 degrees, and that's ohms. Now that I have Z1 and Z2, I can see that Z1 is going to be in series with Z2. So to find my total impedance, I'm going to have to add Z1 and Z2 together. We can't add polar quantities together, but we can add rectangular quantities together. So in order to combine Z1 and Z2, we're going to have to write both of those in rectangular form and then combine them together. So to get our total impedance, we're going to add Z1 and Z2 in rectangular form. Z1 we already have in rectangular form, it's right here. So there's Z1. For Z2, you're going to have to convert this to rectangular form. Once you do that, you'll get 338.6 minus J 340.02. Once you have converted both of the impedances to rectangular form, you can add them together and just remember to add like terms. So we're going to take the 1000 plus the 338.6. We're going to take the minus J 318.31 and combine that with minus J 340.02. And then we're going to take that result, which will be in a rectangular form, and convert it back to polar. So what I encourage you to do right now is to hit pause, get your calculator out, and make sure that you can do every single calculation that you see on the screen. Make sure that you can understand each step, make sure you can type everything in correctly, make sure you can get the answers that are shown on the screen. Now that we have the total impedance, and we have it in polar form, we can move on to the total current in the circuit. Total current is always going to be found using Ohm's law, where we take the source voltage and divide by the total impedance. The source is given as 10 at an angle of 0 degrees. We have our total impedance from the previous slide. We can calculate total current using that information. The phase difference between the total current and the source is just the amount of phase difference you see in the total current right here. The total current is leading the source by 26.16 degrees. We know that because this is a positive value. So this is the phase difference between your source voltage and your total current. Next, we're going to use the total current to find the voltage drop across each individual component. So the voltage across R1, then C1, R2, and C2. We're going to start with the voltage across R1. We're going to use Ohm's law. We know the total current in the circuit, so we're going to use Ohm's law to figure out the voltage drop across R1. So the voltage across R1 is going to be the total current times the value of R1. Just remember to write everything in polar form so that we can easily multiply these two quantities together. So you're going to write your current, which is 6.71 at an angle of 26.16 degrees, and that's milliamps. And we're going to multiply by the value of R1, which is 1 kiloohm with a phase angle of 0 degrees. So when you make this multiplication, you'll get the voltage across R1, which comes out to be 6.71 at an angle of positive 26.16 degrees volts. We can do the same thing to figure out the voltage across C1 because C1 and R1 are in series and they have to have the same current. So we're going to use Ohm's law once again to find the voltage across C1. We're going to take the total current and multiply by the impedance for C1. We calculated the capacitive reactance, and we're going to make sure that we write that in a polar form. So the impedance for C1 is 318.31 at an angle of negative 90 degrees ohms. When you do that calculation, you will get the voltage for C1. Now, quick reminder here, when we calculate these voltages, remember that this is a phasor. This value represents the peak of the voltage wave that you're going to measure across C1. Its peak value is 2.14 volts, and it's going to lag the reference by 63.84 degrees. So try to keep that picture in your mind. If the voltage source has a sine wave that goes right through the reference, it's going to have a peak voltage of 10 volts. Your capacitor is going to have a sine wave that's going to lag by 63 degrees, and it will have a peak value of 2.14 volts. Next, we're going to find the voltage across R2, which is equivalent to the voltage across C2 because they're in parallel. To do this, I decided to set up a voltage divider. And in order to set up a voltage divider, I'm going to look at Z1 and Z2 as a combined group. So Z1 we know is the combination of R1 and C1. Z2 is the combination of R2 and C2. So I'm going to look at this from the perspective of Z1 is in series with Z2. And when I set up my voltage divider, I'm using that perspective. So when I set up the voltage divider, I want the voltage across Z2, which is going to give me the voltage across what Z2 is replacing, which is R2 in parallel with C2. So I'm going to set up a voltage divider where I'm going to calculate the voltage across Z2. So to set that up, I'm going to have Z2 divided by ZT, because that's going to be my total series resistance. And I'm going to multiply by the source voltage. This is how I'm going to set up the voltage divider. And then remember to do the phasor math. We're going to divide these two magnitudes. And we're going to subtract the angles. Keep in mind, I have written the top, the numerator, in ohms, and the bottom is in kilo ohms. You must always pay attention to your units. Don't just look at the numbers and start typing things in. So we have 479.86 ohms divided by 1.49 kilo ohms. So we're going to do this division here and then multiply by the 10 volts. That's going to give you 3.22. And then you're going to do the phase angle. That's going to give you the voltage across R2 and C2. Now we're going to find the current through R2 and C2 in polar form. And there's more than one way to do this. You can set up a current divider, or you can use the voltage that you've already found for R2 and use Ohm's law. I decided to use Ohm's law. If you set up a current divider, though, that will also give you the exact same answer. Here's Ohm's law. We know the voltage across R2, and we know the value of R2's impedance, so I'm simply going to use Ohm's law to figure out the current through R2 by dividing them. So take the voltage that we found on the previous slide for R2, divide by the impedance of R2. Remember, this may feel redundant, but we're always going to write everything in polar form, so make sure you have that phase angle of 0 degrees for your resistor too. Complete the division and you'll get the current through R2. We're going to also use Ohm's law to find the current through C2. So take the voltage that was calculated across C2, which is the same as the voltage across R2, that's the same value, and divide by the impedance of C2. Remember, we're going to take the capacitive reactance of C2 and write it at a phase angle of negative 90 degrees. That's always going to be true when you write the impedance for a capacitor. Now we're going to do the phasor diagram showing the source voltage and the voltage drop across every component. So first we have the source voltage, which is 10 at an angle of 0 degrees volts. Here's VR1 in blue, 6.71 at an angle of 26.16 degrees. So the voltage across the resistor is leading the source by 26 degrees. And then we have the voltage across C1, which is lagging by 63.84 degrees and has a peak value of 2.14 volts. So here's our phasor diagram representing the sine waves that we would be able to measure if we built this circuit on the breadboard or in multisim and were able to hook up an oscilloscope to each component. So that was the first example. I'm just going to do two more examples to go over all of the tools for analyzing a series parallel RC circuit. So here's our second example. We're basically going to do the same thing as the first example. We're going to find the total impedance and the total current. We're going to find the voltage across R1, the voltage across C2 in polar form, the phase difference between the total current and the source, and then a phasor diagram of the currents, the total current, the current through R1, and the current through C2. So we're going to start with total impedance of the circuit. So I have two branches in this circuit. The first branch is a series combination of a resistor and a capacitor, R1 and C1, and then we have a second branch which also has a resistor and a capacitor. So I'm going to start by combining the first branch in series. We're going to combine the second branch in series. Then we're going to take those two values and combine them in parallel. So let's start by finding the capacitive reactance for each capacitor. The frequency is given as 2 megahertz, so you're going to plug that into the equation along with each capacitor value provided. And now that we have XC1 and XC2, we can find the total impedance for the first branch and the second branch. So Z1 is going to be R1 minus J XC1. Fill in your values for R1 and XC1 and convert it to polar. I'm going to do the same process for Z2. So now I know the total impedance of this branch and I know the total impedance of this branch. How do I combine them in parallel? Well, you would treat this the same way you would treat two parallel resistors. So you'd have to take the inverse of each branch, add that together, and then take the inverse of that sum. Or you can use what's called the product over sum rule, which accomplishes the same function. And that's what we're going to use here, product over sum. So when you have two impedances that are in parallel, particularly when you have two impedances that are made up of a combination of things, like this impedance is made up of a resistor and a capacitor. So once you've combined these resistors and capacitors together, you're now left with a Z1 in parallel with a Z2. If you have two parallel impedances, you can combine them using the product over sum rule. This is the product over sum rule. It literally means what the name says, product over sum. Product divided by sum. Now, in order to do the product over sum rule, you're really going to have to be comfortable going from polar to rectangular and back again, because in order to carry out all of these mathematical operations, we're going to need both. So let's start with the numerator. We're going to fill in what we know for Z1. We're going to fill in what we know for Z2. On the denominator, we're going to fill in what we know for Z1, fill in what we know for Z2. Now we're going to start with the denominator. We're going to have to add these two quantities together. They're currently in polar form. We can't add quantities in polar form. They must be in rectangular form. We're going to have to take each term, convert it to rectangular form, add it together, then go back to polar, and then we will be able to complete the problem. So there's a lot of steps here that involve polar operations. So let's start with the bottom. Convert the first term to rectangular, and you'll get 33 minus J, 79.58. Convert the second term to rectangular, and you'll get 47 minus J, 36.17. So I'm taking the first term in rectangular and adding the second term in rectangular. So what I want you to do is add these two terms up, add the 33 plus 47, add the minus J, 79.58, and the minus J, 36.17, add those together, convert it back to polar, and make sure you get this value shown on the screen. That's where this value comes from. Adding these values up, going back to polar. Also, look at the numerator. We're going to multiply these two polar quantities together, multiply the magnitudes, so multiply the 86.15 times the 59.31. That'll give you 5,110. And then add the phase angles together. So you have a negative 67.48 plus a negative 37.58. That's how you get negative 105.06. Now that we've simplified the top and the bottom, we can perform the division. 5,110 divided by 140.71. That gives you 36.31. And we can do negative 105.06 minus negative 55.35 degrees. That gives you your phase angle. And there's your total impedance for this circuit using product over sum. Product over sum will always work even if you have a resistor in parallel with a capacitor. The formula that we're using is just a variation of product over sum. So anytime you have two impedances in parallel, this will always work as long as you set it up properly and carry out the addition and multiplication properly. And now we have our total impedance in the circuit. Another thing to watch out for when you set up your product over sum, make sure everything has the same units. Ohms, 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 ohms. Make sure that you're paying attention to units always. If the top is in ohms and the bottom is in kilo ohms, your answer will not be correct. So now we have the total impedance of this circuit. Now we can find the total current using Ohm's law. Voltage divided by total impedance gives you total current. And the phase difference between the total current and the source is the 49.71 degrees. So the total current is leading the voltage source because this is a positive angle. If this were a negative angle, we would say it's lagging. Next, we're going to find the voltage across R1 and C2 in polar form. There's more than one way that you could go about this. You can find the current through each branch and then use Ohm's law. Once you know the current through R1, you can take the current through R1 multiplied by its impedance and you have the voltage across R1. Or you can do a voltage divider because the voltage from this point to ground is equal to the source, and that voltage is going to divide between the resistor and the capacitor. So that's two options you could use to figure out the voltage across R1 and the voltage across C2. So I'm going to start by finding the current through R1. I know the current through R1 is going to be the source voltage divided by Z1. I know that because I know the voltage across C1 from this point to ground. The voltage across Z1 has to be the source because it's in parallel with the source. So I know the entire voltage across Z1 and I know the value of Z1, so I'm going to use Ohm's law to find the current through Z1. Fill in your source voltage and your impedance for Z1 and you'll get that current. And now that I have the current, I can use Ohm's law to find the voltage for R1. So I'm going to take the current through R1 and plug that into our Ohm's law equation, as well as the impedance for R1. And here's our voltage for R1. Next, I'm going to find the voltage for C2, and instead of using Ohm's law and finding the current through C2, I'm going to use a voltage divider. So I know that the voltage across Z2 has to be equal to the source because Z1 and Z2 are both in parallel with the source. So I know that voltage has to drop across Z2. And since I know that voltage, it divides among R2 and C2. So I'm going to set up a voltage divider to figure out how much of that voltage that is applied across the entire impedance Z2, how much of that voltage is divided among capacitor 2. So to set up that voltage divider, I have two elements in series, and I want the voltage across the second element. So my numerator is going to be the total impedance of the capacitor. My denominator is going to be the total impedance of this branch, not the total impedance of the circuit, because I'm dividing the voltage basically from this point to ground. That's what I'm looking at. And a voltage divider has to be applied to elements that are in series. So my numerator is going to be the impedance of capacitor 2. My denominator is going to be the total impedance of this branch, and I'm going to multiply by the voltage applied to the branch, which is the source voltage in this case. So once I set up my voltage divider and perform the calculations, I'll get the voltage for C2, shown here on the screen. Next, we're going to do a phasor diagram showing the total current, the current through R1, and the current through C2. If you look at our calculations, we haven't yet calculated the current through C2, so we're going to have to calculate that first. We already know the current through R1. We calculated that in the previous slide. That's a recap. And to calculate the current through C2, we're just going to use Ohm's law again. We're going to take the source voltage, which is applied to impedance Z2, and divide by Z2. That'll give us the current through Z2, which is also the current through R2 and C1. And then we can draw our phasor diagram. Notice that none of our phasors are aligned with the origin. They're not aligned with the reference. So I did draw a little XY axis just as a reference point so that you can see each angle for each phasor very clearly. Remember, when you draw your phasor diagrams, your magnitudes should match your drawings. So IT is the largest value, therefore it has the longest vector. So that's our second example for series parallel RC circuits. And here's our third example. We have a ladder network where we're going to, again, calculate the total impedance, the total current, the voltage across R1, R2, R3, and C1. We're going to look at the phase angle for the current, and then we're going to draw two phasor diagrams, one for all of the voltages in the circuit and one for all of the currents in the circuit. We're going to start with the total impedance of this circuit in polar form. So to begin, we're going to look at the relationships. If you think about how current will flow through this circuit, current will flow through C1 and split. Some will go through R1, some will go through R2. Whatever goes through R2 will go through R3. V out, this is just like a probe. This is not really part of your circuit. Current is not flowing here. The current that flows through R2 is the current that flows through R3. So R2 and R3 must be in series. Once you combine R2 and R3 in series, that combination is in parallel with R1. Once you combine that combination, you now have an impedance that is in series with your capacitor. So there are our relationships. We're going to start by collapsing those resistors. So we have R1 and R2 are in series, combine them first. Then take that quantity and combine it in parallel with R1. So when we combine all three resistors, we get a total resistance of 1.05 kiloohms. We also can calculate the capacitive reactance of that capacitor using the 100 hertz provided, and you'll get 3.39 megaohms as your capacitive reactance. Once we combine all of those resistors are then in series with the capacitor. So our total impedance is just going to be the combination of the capacitor and the resistor impedances in series. We're going to combine them using the same formula that we use for a resistor and a capacitor in series. So we have RT minus JXC. Notice that I converted all of the units to megaohms and then converted it to polar. Now that we have the total current, we're going to find the total, now that we have the total impedance, we're going to find the total current using Ohm's law. And we can see that the phase angle leads by almost 90 degrees, 89.98 degrees. So we have the total impedance, we have the total current, and we have a phase angle for the total current. Next, we're going to find the voltage across R1, R2, R3, and C1 in polar form. Let's start with C1. We can use Ohm's law because the total current in the circuit is the current going through C1. So we can say that the total current multiplied by the capacitive reactance is going to give us the voltage for C1. Keep in mind your current is in microamps and your impedance is in megaohms. So you're going to come out with 4.98 volts. So that voltage across the capacitor is almost identical to the source. So the capacitor really dictates most of the behavior in this circuit. Those resistors don't have much pull on what's happening. The capacitor is dominating the behavior of this circuit. Now we're going to find the current through R1 using a current divider. So to set up our current divider, think about it as if you have two paths. The path through R1, the path through R2 and R3. I want the current for the path that goes through R1. So the numerator of my current divider is going to be the combination of my two parallel paths. So when we added R2 and R3 together and then combined that in parallel with R1, that became your total resistance in your circuit, not your total impedance, but your total resistance. And that's the total resistance you're going to use for your current divider in the numerator. The denominator will be the resistance for R1, and we're going to multiply by the total current going into this node before it splits. The total current going into this node also happens to be the total current in the circuit. So that's how we set up our current divider. And now that we have that current divider, we can make these calculations to get the current that you see on the screen, 0.701 microamps. That's the current through R1. Then I can use that to find the voltage across R1 using Ohm's law. Next, I'm going to find the current through R2 and R3 using a current divider again. So when I set up the current divider, again, I have two paths. Here's my first path, here's my second path. The numerator of my current divider will be the parallel combination of my two paths, which is the total resistance we had before. The denominator of my current divider will be the total resistance of this path. The total resistance of the second path is R2 plus R3. And then we're going to multiply that by the total current going into this node before it splits. So that's how we set up the current divider. And when you make these calculations, you'll get the current through R2 and R3. And then we can plug that current into Ohm's law to find the voltage for R2 and R3. Now, R2 and R3 are not in parallel, but they have the same voltage. They have the same voltage because they have the same resistance value and the same current going through them. So that's why you see the exact same answer twice. Alright, so this pretty much solves the problem. The only thing left is to draw the phasor diagrams. I'm going to leave that up to you to draw those in your notes before you turn them in, just so that you can get some independent practice on drawing the diagrams. Make sure that you use the voltages that were calculated here and the currents that were calculated here to draw your phasor diagrams. And I'll look for those in your lecture notes when you turn them in. So that pretty much sums up the video for series parallel RLC circuits. A lot of what we're doing is looking at the circuit the same way you would look at a resistive circuit. That's a series parallel circuit. But now we have to think about the impedance of a capacitor, the fact that we have an AC source, and the fact that now we're dealing with polar and or rectangular quantities, which makes the math just a little bit more complex than a regular series parallel circuit that only has resistors. So some of the best advice I can give you is to practice, practice, practice. The steps get easier, the math goes faster, the more that you practice. So go through the homework problems, ask questions if you're not sure. Also use Multisim to check your work. As you're going through the pre-labs for this class, you should be learning how to build these AC circuits in Multisim and using a voltage probe or a current probe to check your work. Feel free to do that on any homework assignment as well. If you notice that your Multisim results don't match up with your calculations, that's a chance to ask questions and review your work. As always, please email me or send me a message if you need help, and I'll be happy to assist you. And that is the end of this video.